Section 3.1, this is test to review. Are the following relations a function? So the first relation is a number of ordered pairs. And if I want to graph that correspondence, I can create a correspondence really quick here so you can visualize. So -3 in the domain, 2, 4, 8, and 10. In the range we have 1, 4, -2, another 4, and then 5. So we don't repeat. Now, -3 is mapped to 1, 2 is to 4, 4 is mapped to -2, 8 is mapped to 4, and 10 is mapped to 5. As you can see, this is clearly a function. So this is a function. And I now can erase my work and test the second relation. So I'm going to create another correspondence. -3, -2, 2, and then the range is -4, 9, -8. -3 is mapped to -4, -2 is mapped to 9, 2 is mapped to -8, and 2 is mapped to 9. So as you can see here, this is not a function. 2 has 2 elements in the range that are mapped to 2. So this is clearly not a function. So I will erase the correspondence, which is my work. Question number 2, evaluate f of x is equal to x squared minus 2x minus 5 at each of the following values. Evaluating is basically when you plug the number instead of x. So f of 3 is basically you remove each x and put a placeholder there, and then you're going to put the 3 in there. Now I'm going to compute 3 squared is 9 minus 2 times 3 is 6 minus 5. And then we do the operations from left to right. 9 minus 6 is 3 minus 5, which is going to give you -2. So that is the final answer. The second one, again, I will remove the x and I will place a placeholder, and then I will plug -2 in there. -2 squared is +4 minus 2 times -2 is +4 as well. So +4 minus 5. 4 plus 4 is 8 minus 5. 8 minus 5 is 3. And the last one, I will remove again x and put a placeholder there. And then I will plug the -x inside. -x squared is +x squared. -2 times -x is +2x or +2x, and then -5. And that is the final answer. If f of x is equal to 5x minus 3, number 3, we need to evaluate f of -1. f of -1 is, I will remove the x and put a placeholder and replace the -1 in there. 5 times -1 is -5 minus 3. -5 minus 3 is -8. And we want to solve f of x is equal to 4. So in order to solve that, I will look at this equation and I will replace f of x with 4. So this is going to become 4 equals 5x minus 3. Now this is a linear equation. I can solve by adding 3 to both sides of the equation first. I will get 7 equals 5x, and then I will divide by 5. So this will lead to x is equal to 7 over 5. So that is the solution. Number 4, let f of x is equal to x squared plus 2x. We want to evaluate f at -2. So again, I will remove all of the x's and put a placeholder instead. And then I will put the -2 inside of the placeholder. Now I will evaluate. -2 squared is 4, plus 2 times -2 is -4 or -4. 4 minus 4 is 0. Now we want to solve f of x is equal to -1. Again, I will take this f of x and replace it there, so it's equal to -1. So -1 equals x squared plus 2x. Notice how this is quadratic. So I will have to make the left-hand side 0. I'm going to add 1 to both sides of the equation. So I will end up with x squared plus 2x plus 1 equals 0. And then I can solve it using the quadratic formula. Or I can basically factor. So if I factor this, I will have x and x. I need two numbers. Their product is 1. Their sum is 2. That is 1 and 1. So now I can say this is the same as x plus 1 all squared equals 0. If you take the square root for both sides of the equation, you're going to get x plus 1 equals 0, which now we can solve by subtracting 1 from both sides of the equation, and we get x is equal to -1. So that is question number 4. Determine whether the graphs are graphs of functions. In order to determine if a graph is a graph of function, we will use the vertical line test. The vertical line test states that if the vertical line cuts the graph at one point only, then the graph represents a function. If it cuts it in more than one point, then it is not a function. So the first one is clearly a function. The second graph, as you can see, the graph here intercepts the vertical line at 2 points, so this is not a function. The last graph, I will use the vertical line test, and as you can see, the graph intercepts with the vertical line at 1 point only, so this is a function. So we use the vertical line test to determine if it's a function or not. Does the relation represented in the table from below represents y as a function of x? Let's see here. So as you can see, 20 is mapped to 2, 14 is to 10, 21 is to 11, so the first one is a function. 19 is mapped to 2, and I have two 16s, so I'm just going to use one of these. And this is mapped to 12 and to 7, so that is not a function, because 16 here has two images. Question number 7. So the table below is basically a function, represents the function f is represented in the table below. We need to evaluate f of 3. So this basically says when x is equal to 3, what is the value of y, or what is the value of the function? So here is when x is equal to 3, the value of y is 20. So f of 3 is equal to 20. The second question says that when f of x is equal to 32, what is the value for x? So when y is equal to 32, in other words, what is the value of x? So here is when y is equal to 32. The corresponding x is 7. So the answer is 7. So solve f of x is equal to 32. That is, x is equal to 7. When we say solve, that means we need to find the value of x that makes this function true. So the value of x is 7 because f of 7 is 32. So we're working backwards. Why does the vertical line test tell us whether the graph of a relation represents a function? because it tells us whether one value of x is mapped to two values or one value only. For example, if you look at this graph, we know that this graph is not a graph of a function because one value for x, when this is x, it has two values for y, corresponding values for y1 and y2. And we know that is not a function. That's not the definition of a function. So that's why the vertical line test works. Section 3.2, determine the domain and range of the function. We know that the domain is equal to all of the x values if it's represented as a group of ordered pairs or a set of ordered pairs. So that is 8, 6, -7, 10, and -1. It doesn't matter the order. And the range is the set of all of the y values if it's represented as a set of ordered pairs. So this is 7, 4, 8, 3, and -2. B is actually not a function, so you don't need to find the domain and range for B. It's not a function because 11 has two images, which is 9 and 5. So this is not a function, which means we don't need to find the domain and range. How do we determine the domain of a function defined by an equation? We basically find all of the points that make the function undefined and eliminate them from the domain. So we find all of the values that make the function undefined and eliminate them from the domain. That is basically how we find the domain. So how does that work? Let's answer question number 3. We want to find the domain of the function. Notice how I have a denominator in this case, and we said whenever we have a denominator, we find any points that make the denominator 0. So we're going to set the denominator equals to 0 and solve that equation. So we get x is equal to 9. Now, we don't want x to be equal to 0, so we set the denominator not equal to 0. So we know that the domain now is all of the real numbers except for number 9. How do we see that and how do we write it as an interval? Here is number 9. I'm going to put a circle on it, which now is going to make my domain, or it's going to cut the domain into two pieces, two intervals. The first interval is from -infinity to 9, and the second interval is from 9 to +infinity. And all we need to do now is to put the union sign between them. Now that is our domain basically. The domain is all of the real numbers except for 9, and as an interval notation, it is going to look like that. Same with this one. So we're going to set 2x is not equal to 0. And now we can divide by 2 both sides of the equation. So we have x is not equal to 0. So we're going to eliminate the point 0 from our domain. Same manner. Here is the 0. So now we have two intervals. The first interval is from -infinity to 0, and the second interval is from 0 to +infinity, and we make the union sign in between, and that is going to be the domain. The next question, notice how this is not factored, it will be easier to factor that denominator. So first, we're going to set the denominator not equal to 0, x squared plus 2x minus 15 not equal to 0. And I'm going to treat the not equal as an equal sign. So I'm going to treat it as an equation. So the left-hand side is going to be factored, not equal to 0. So this is going to be x and x. I need two numbers. The product is negative 15, and their sum is positive 2. That is positive 5 and negative 3. Positive 5 and negative 3. Now, if we want to solve, we're going to set each factor equal to 0 and solve, or not equal to 0 and solve. So this is going to give me x is not equal to 3. So that is our first point that we need to eliminate. Next one, x plus 5 not equal to 0, and that is going to give me x is not equal to negative 5, and that is the second point that I need to eliminate. On the number line, I will arrange my points from smallest to greatest, from left to right. So here is negative 5, and here is 3. Basically, I will put them in the right order on the number line. Now, what that does, it's going to create 3 intervals. The first interval is from negative infinity to negative 5. The second interval is from negative 5 to 3. And the third interval is from 3 to positive infinity. I'm going to put the union sign in between. And that is basically the domain of this function. I'm going to do the next one. So we're going to set x squared minus 9 not equal to 0. Now I'll use the property, the square root property. So I'm going to add 9 to both sides of this equation. I'm treating this as an equation, basically. So x squared is not equal to positive 9. Now I'll take the square root for both sides of the equation. Don't forget the positive and negative. So x is not equal to positive and negative 3. So I have 2 points to eliminate, 3 and negative 3. Again, on the number line, I will put negative 3, and I will put 3 in the correct order. And now I have created 3 intervals. The first interval is from negative infinity to negative 3. The second interval is from negative 3 to 3. The third interval is from 3 to positive infinity. I'll put the union sign in between, and that is the domain for this function. When we have a square root, we don't want to have a negative number under the square root. Also, we can have 0. So in order to find the domain, we're going to set 2x minus 6, which is the radicand, greater than or equal to 0, and then solve that inequality. We're going to add 6 to both sides of and that is going to give me 2x is greater than 6. Now I can divide both sides by 2. So I will end up with x is greater than or equal to 3. Now I will write this interval, this inequality as an interval. Here is 3 and it's closed circle, and we need all of the x's that are greater than 3, which is basically this interval right here. And that interval is from 3 to positive infinity. So the domain for this function is from 3 to positive infinity. Similar, the next one, I will set 6 minus 2x is greater than or equal to 0. And now the easiest way is to add 2x to both sides. So now I have 6 is greater than or equal to 2x. I will divide both sides by 2. So now if I rewrite this, it's going to be 3 is greater than or equal to x. I'm going to flip it so you can see it. So less than or equal to 3. All I did is just flipped it. And now that is the interval. So here is the 3 and it's closed circle. It's all of the x's less than or equal to, which is going to give me this interval. This interval is basically negative infinity to 3 included. So that is the domain of the last function. Question 1, part B. I just wanted to mention that